concepts that we're going to talk about today that are important. Okay? First thing, we'll talk about why this is entitled the real number system. It is entitled the real number system because there is a whole nother system of numbers called the imaginary number system. You won't have to deal with them until like second or third year university math or physics. So most of you will never have to deal with an imaginary number. Suffice to say they do exist. Well, kind of. They're imaginary. But the numbers we use are the real number system. And that's exactly what this is. These are what 99% of the world uses for math. There's a small group of people that deal in imaginary numbers, but there are not many. All right, we will start with the natural numbers. Now, all of these are something you should at least be aware of the definition of them. We'll start with the natural numbers. The natural numbers are what I like to call the counting numbers. Okay? So if I said, class, let's all count to 10 together, how would we start? What would be the first thing we all said? 1. But 1 is not the first number, is it? What is the real first number in our number system? 0. Goes from 0 to 9, and then it starts over again, right? That's what it means, 0 to 9, and then the next number is 10, which is one group of 10 with 0 left over, right? So, but we don't count 0, do we? So if I said, let's all start counting, we wouldn't go 0, 1, 2, 3, 4. We wouldn't. We'd start with 1. So the natural numbers are the counting numbers. They go from 1, 2, 3, up to what? Where do our numbers end? Infinity. So they don't really end, right? But it goes up till that point. Everybody cool? I know it's weird to say that infinity is part of the real number system because infinity doesn't really exist. You'll never get to it. You understand what I'm saying? But it's there anyway. Everybody good? Easy peasy. 1, 2, 3, 4, 5, and so on. The whole numbers. Now, you people know whole numbers because you've talked about fractions. It's not what whole numbers actually are. Whole numbers are the natural numbers plus 0. So whole numbers are 0, 1, 2, 3, up to infinity. Everybody good? Easy peasy, right? There's no skill involved. It's just something you got to remember. Hey, Kirit. See, I on purpose didn't mark you as absent because I knew you wouldn't have given up. But tomorrow, if you're this late, I'm marking you as late. All right. Then we get integers. Integers, guess what? Are the natural numbers plus negatives. So it's negative infinity, negative 1, negative 2, 0, 1, 2, positive infinity. Is everybody cool? Everybody understands? This is the first main 3. Put a line there because those 3 share some characteristics. And the characteristics they share are as follows. There are no fractions. And if there's no fractions, are there decimals? No. No decimals. Pen stopped working for a second there. No decimals in any of these 3. Okay? Why is it important that we discuss this? Because it's possible in math that you will be dealing with things that do not have decimals and fractions. Understand? For example, if I was doing a graph of no, that's a bad example. Let me think of one. If I were doing a graph of the amount of kids that were in my class on any given day, could there be a fraction? No, of course not, because half a kid cannot come to class. Do you all understand that? So that's why we have all these categories, because sometimes you need to have those categories. If I was measuring time, could I ever have a negative number? No, because I can't go back in time. So that's why these exist. Everybody cool? All right. Now, we move on to rational numbers, which are slightly more difficult. Rational numbers are all the above plus all fractions plus all repeating decimals. So, this is the way we write it in math class. Rational numbers are any number that you can write as x over y. Y cannot equal 0, and x and y must be integers. Okay? So I'm going to put a couple of examples here, make sure you understand what I'm saying. Is this allowed? Is that a rational number? Is it x over y? Is x and y both integers? So we're good, right? Is this a rational number? Why? What is it actually? 7 over 1, right? This is technically 7 over 1. Everybody cool? Okay, what about this? 2.5 over 7. Is that a rational number? As it's written right now. No, why not? It's a decimal in the numerator, yes? Now, what if I multiply this by 10? Then what do I get? What do I get then? 25 multiplied by 10 over what? 70. Is that a rational number? Yes. So remember, this technically isn't rational unless you change it over. Is everybody good? Everyone's good up to there? All right. The only things we haven't covered now are irrational numbers. And irrational numbers are everything else. So no non-repeating decimals. All right. If you're a non-repeating decimal, you're an irrational number. What's the most famous irrational number? Pi. Because pi is 3.14159, so on, so on, so on, for billions and billions and billions and billions and billions of decimal places. And so far it hasn't repeated. So we're reasonably sure it won't. That's the most famous one. There's a bunch of other ones. You don't need to worry about any of them until at least grade 11. No, I lie, grade 12. E is another famous one, yes. Okay? But there are irrational numbers that you do need to worry about. And the irrational numbers that you need to worry about, we are concerned with these square roots I shouldn't say square roots, all roots that aren't perfect. And what do I mean by that? Well, what's the square root of 4? 2. Perfect square root. Easy peasy. Right? What is the square root of 2.25? Does anyone know? It is indeed 1.5. It's a decimal that ends. So that's okay. Everybody cool? What, though, happens if we do the square root of 3? What do we get? Square root 3. My whole screen fills up. Does it repeat? It looks like it might, 0808, but it does not. These guys and all of their friends are irrational. We cannot give them a value. All we can do with them is simplify. All right? So square root of 5, square root of 7, square root of 10, square root of 11, so on, so on, so on. Everybody cool? If the square root fills up your whole screen on your calculator, 99.9% of the time it is an irrational number, which means we cannot assign it a proper value. All we can assign it is an approximate value. Everybody good? All right. Turn the page over, and let's remind ourselves of how to do these things. This is just grade 6 place value, right? 0.12 is what? That is 12 over 100, because that is the tenths, and that is the hundredths. Now, in Mrs. Bag Crumble's grade 3 class, would you ever have been allowed to leave that as a fraction? No. What would you do with it? She or he would have said reduce it. But you're not really reducing, are you? So reduce means make something smaller. We've all seen Ant-Man. When you reduce something, it gets smaller. But I'm not reducing this because the fraction I'm going to end up with is the exact same fraction, isn't it? So what we're actually doing is simplifying. Everybody calls it reducing because both numbers are getting smaller, but I find that to be slightly confusing because both numbers are not getting smaller, because this is a ratio, 12 out of 100. So what we're actually doing is making it simpler. We are going to divide both by 4 to get 3 over 25. Everybody remembers how to do that, yeah? Okay. Now I got to talk about that little line right there. What does that line mean? It means part of this repeats. What part? The 1. So this is technically 0.111111 for how long? Ever and ever and ever. So math guys being lazy devise this trick. They write it that way. How do I turn that into a fraction? Somebody knows. What do I do? Nobody knows? What do I do, Prusia? Yeah. What is the rule of 9? Yeah, I go over 9. 1 over 9. And if I do that on my calculator, 1 divided, oh, not 19, you idiot. 1 divided by 9. 0.1111111. Can anybody tell me why? Can you tell me why? Why it works? Or did your teacher just say, you just divide by 9? Okay. Let's talk about why it works, because it's kind of important. Since this repeats, we know that it's going to be a rational number, don't we? And if it's a rational number, we know we can write it as a fraction, correct? Everyone agrees? Okay. So, if this little bar wasn't there, then what is that as a fraction? That's 1/10. Agreed? This is why the rule of 9 works. That would be 1/10. Yes? Everyone agrees, right? Okay. Now, is 0.111111111 bigger or smaller than 0.1? You would rather, what's bigger, a dime or 11 cents? 11 cents is bigger. So 0.111111 is bigger than 0.1, isn't it? Jimmy, you're shaking your head. Why? If I had a dime, which is 0.10 of a dollar, and you had 11 cents, which is 0.11 of a dollar, who has more money? You or me? This is me. This is Jimmy. Who has more money? You do. So, that must mean that 0.11 is bigger than 0.1, right? So that must mean that 0.11111 is bigger than 0.1, right? Okay. So, if this equals 0.1, right? And I have 0.11111 repeating, well, that must equal, it's a 1, but it can't be over 10 because that would be the same as this, yes? But it has to be a rational number. So this down here has to be an integer, doesn't it? Right? And the next integer that is bigger than 1/10 is what? 1/9. That's why it works. Is everybody cool? Because I can't put 1/10 because that's 0.1. And 1/9, because it's fractions, is bigger than 1/10. Just like 1/3 is bigger than 1/4. Everybody good? Okay. That's why the rule of 9 works. Prush's math teacher called it the rule of 9. I don't call it that. I just say this is what happens. Everybody good? All right. Now have a look at C and tell me if C is different than B in any way. Some people are shaking their heads, some people are nodding. Is C the exact same thing as B? Most people are nodding now. Why are you nodding? What is happening in C that makes you say, oh yeah, it's the same as B? There's, the 2 is repeating, isn't it? Do we know that it goes on forever? How? The 3 dots? Do the 3 dots technically mean that the 2's go on forever, or do the 3 dots mean that the decimal continues? It's a very technical thing. It just means the decimal goes on. Technically. So this, we don't know if the 20 billionth decimal point here is going to be a 2. Understand? So for this one, we are making an assumption. And the assumption is that it is 0.2 repeating. Now, if it is 0.2 repeating, when it was 0.1 repeating, it was 1 over 9. So when it's 0.2 repeating, what's it going to be? 2 over 9. Is everybody good? Yeah? All right. Now, look at D and tell me what's different. Pardon me, Charlotte? The 5 doesn't repeat, but the 4 does. So what do you think? And some of you will already know. What is that? Since the 4 is repeating, we must be able to write this as a fraction, yes? Because we know it's rational. How? Does anybody know how to do that one? I'm betting that everybody has seen it done at least once but can't remember how to do it. Is there anybody that can remember how to do it? All right. Well, let's talk about it then. What is this really? Like, how would I write it if I had an endless amount of time and an endless amount of energy? I would write 0.544444444. Agreed? But we're not sure what to do with that, are we? What would happen if I multiplied this by 10? What would I have? 5.44444 forever. Agreed? Now, if I wanted this as a fraction, now the only thing that's repeating is the 4's, correct? How do I do this part as a fraction? It would be 4 over 9, wouldn't it? Everyone agree? Now, 5 would be out in front, yes? How would I turn this into a fraction? What do I do with the 5, 9, and the 4 if I want this as a fraction? I do times plus, correct? And I end up with 49 over 9. Agreed? Everyone agree? Right? Okay. Now, my original fraction was 0.544, wasn't it? I multiplied by 10 to get to 49 over 9, didn't I? So I don't need 49 over 9. I really need 49 over what? 90. And now I'm in business. Let's check. 49 divided by 90. 0.54444444444. Does everyone see how to do it? What if I gave you 0.234444 and only the 4's were repeating? What would you do? I'd multiply by 100, wouldn't I? To get what? 23.444, which would be 23 and 4 ninths, times plus 9 times 23. 9 times 20 is 180, 207, 211 over 9, yes? But is it 211 over 9? No, because it was over. I had to multiply by 100, so it's 211 over 900. Can everybody do it? Ease bees lemon squeezy, right? Right? Okay, so let's use our calculators to do this. Now, I am betting that some of you are going to be unable to remember how to do A on your calculator. Skip it. I'll come back to it in a minute. Everybody else, use your calculator, if you need to tell me which categories these numbers fit in. Now remember, if you're a natural number, are you automatically a whole number? Are you automatically an integer? And are you automatically a rational number? Yes. If you can get something to natural, everything else counts. Everybody good? Go. It should take about 30 seconds to fill in page 86. If you need to use your calculator, go ahead. Again, you may not remember how to do A. Okay. What's b? B is a natural number. Why? Because the square root of 25 is 5. Do I hit 5 when I start counting? 1, 2, 3, 4, 5. So it's natural. That automatically makes it everything else. What about C? Pardon me, Erlen? Irrational? Why do you think so? Because it doesn't repeat. Does it end? It ends because there's no dots and no bar. So if it ends, it's what? Rational. Because this is 5 and 319,754 1/millionths. So that is rational. Everybody good? What if I put ... there? Now what is it? Now it's irrational. That's why I use green there. Everybody good? All right. What about D? We just did a quiz on exponents. Everybody should have been able to do this. What's the base here? What does that exponent mean? There's 4 of them. -2 times -2 times -2 times -2. -2 times -2 is +4 times -2 is -8 times -2 is +16. What is it? Natural. What about 9? Natural. What about F? If you punched it into your calculator, what happened? It said error. So what must that be? That is one of the imaginary numbers. Because how could you have a square root of a negative number? Everybody knows that, right? Because square root means 2 numbers that are exactly the same, yeah? What 2 numbers could multiply to make a negative number? There aren't any. Because to get a negative number, they have to have different signs, don't they? And if they have different signs, they are not the same number. So that's imaginary. What about this one? You can guarantee it's rational, or you are assuming it's rational? Right. This is rational assumed. Because we do not know if the billionth decimal place is a 7. Understand? Now, what if I changed that to this? Now what is it? Now it's rational for sure. Is everybody with me on the very subtle difference? Yes? Okay, now, just a reminder up here, cube root of -14. A great many of you probably don't remember how to do these on your calculator because it's a bit tricky. Some of you, if you're really lucky, you have a cube root button on your calculator. Some of you do. Some of you won't. Some of you will have this button on your calculator, X root. So to do this, if you have this button, if you have this guy, you just hit that button, then you hit -14 and equals. But if you have this button, you have to push 3, then this button, then -14, and then equals. Unless you have a backwards calculator, in which you have to push 14, -14, this button, then 3, then equals. It's really not that important in math class because we don't like decimals. But when you get to physics class, you're going to have to use that button a lot. So on my calculator, my fancy one, I don't have that cube root button, so I have to do this. Math, see it's right there, cube root. So I got to go 4, cube root negative 14. Negative 14. My screen has filled up. So what is it? Irrational. Now, I'm not going to worry too much if you can't make it work, all right? We'll spend some time with that at a little later date, okay? Now, I'm going to stop right now because you guys have a test on trig, and this is essentially done. So here's what I want you to do. It's 8:40. Your break is at 9:15. I would like for you, this is very important to me. It actually is. I especially need you to be able to do 3, 6. Actually, I really need you to do this page. Not because I'm going to test you on it so much, but because the ability to work with these numbers is important later on in this class and in grade 11. Do you understand what I'm saying? Whether you have this memorized or not, I'm not too worried about. But this page, the ideas behind it are really important to future. Okay? So I'm not going to do a lot of testing of these exact type of questions on you, but I do want this concept in your head. Everybody good? So here's what I want you to do. I want you to do this page. Of course, you have the answers, so you can check them. I want you to do this page. Then you can prepare for your trig test. All right? Preparing for your trig test means taking a quick look at your work and asking me any questions you might have. Now, you'll notice in your book, I left you a blank page at the end of your trig review. I lie. At the end of your trig lesson, that was test review. If you got any questions about trig, that's where you should be putting them. Does everybody understand? Okay. Now, you have 35 minutes before that break, right? That's a lot of time to prepare for trig and do these like 10 questions I'm asking you to do. Yeah? So, what's going to happen is I'm going to let you work for a while. If it gets to the point where as I'm walking around I'm seeing less work being done than talking, then I'll just move on to number 3 and we'll just pick it up after the trig test, okay? It's not a threat, but if you're all not doing math, then there's no need to sit around. We don't have time for that, okay? Everybody understand? Go. Prime factors are very powerful indeed. You can do a lot of math if you can deal with prime factors. So before we deal with prime factors, we have to remind you what a prime number is. What is a prime number? Nobody remembers. Nobody? Yes, a number that can only be divided by one and itself. Prime number is any number, and I'm lazy, so I'm writing a hashtag instead of the word number because it actually means number. It doesn't mean hashtag. Any number which can be divided by only one and itself. Now, the most powerful prime number is 2. Does anybody know why? There is something special about the number 2. That speciality is 2 is the only even prime. Every other prime number is odd. I would recommend you learn all the prime numbers up to 30 and have them memorized. That would be useful for you in future math classes. They are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. I would recommend you memorize those. Can I test you on that? No, I can't, because that's not a math skill. That's a memorizing skill. And those are two different things. But it will help you if you have most of them in your memory, your working memory somewhere. Okay? Excellent. Now, the next thing we are going to do is we are going to complete factor trees to find prime factors. That means every time we do some division, we're going to be given two factors, right? Because when you divide something, you get two factors. 10 divided by 5 is 2. The factors of 10 are 2 and 5. You all know that already. Every time you do a division, you get two factors. We are going to keep dividing until all of our factors are prime numbers. Okay? Now, if you wish to do what your elementary school teacher taught you, which is fine, you're probably going to do this. You're going to make two little branches, and you're going to put two numbers here that multiply to 54, right? What are the first two numbers 99% of you are going to put there? 9 and 6, right? Are either one of those prime numbers? No. So can we stop our factor tree there? No, we cannot. So we've got to divide again. 9 divides into what? 3 and 3. Are 3 and 3 prime numbers? Yes, indeed. So every time a branch ends in a prime number, I like to circle it because I need all of those prime numbers. There's another one. What does 6 break down into? 3 and 2. And those are all primes, yes? Now, because those are all factors, that means we can multiply them together, yes? And if I multiply them together, I would get 2 times 3 times 3 times 3. And that would equal 54. 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54. But being that we're in grade 10, would we write it this way? How would we write it? 2 times 3 cubed. Everybody good? Everybody agree? All right. Now, how many of you have seen factor trees drawn this way? Terrific. Some of you will have had teachers that wanted you to draw them horizontally. So they might have written 54 and you might have gone this way. 9, 6, 3, 3, 2, 3. You might have been taught that. Any difference? No. That's like saying you wore a blue shirt today and a yellow shirt yesterday. You still wore a shirt. It doesn't matter. Everybody good? Now, there's another way to do this that I like to use, and that is this method. I divide by 2. 2 goes into 5 twice. 14. 2 goes into 14 7 times. 3, 9, 3, 3. And then all your prime numbers live on the outside. Some of you may have been taught that. It depends on how old your teacher was, quite frankly. Everybody okay with doing a factor tree and finding prime factors? Great. Do it for 162. Go. Everybody should be comfortable to there, yes? Yeah? Everyone is good? Everyone was able to make the factory? Everyone was able to write out the factors? Yeah? Pardon me? Oh, Yes. 3 times 3 times 3 is 81. Thank you. All right. Everybody can do this, yeah? Okay. Greatest common factor. You've all seen this before, too. GCF. Doesn't have a lot of use in this unit. Has a huge amount of use in the next unit. So pay attention to what's going on here. A greatest common factor is a number which is a factor of at least 2 other numbers. So, a greatest common factor, GCF, can be found using prime factorization. Here is how you do it. We have our prime factorizations. That was supposed to be green. We have our prime factorizations there and there, yes? Prime factorization will find you a GCF by listing all common factors from the lists. Okay? So here's a list, here's a list. If I write every common one, I will get my GCF. We're going to do it in a second. Actually, we might as well do that right now. Find the GCF, which we're going to highlight in green, of 54 and 162. So the list for 54 was 2 times 3 cubed, right? The list for 162 was 2 times 3 to the 4th. Agreed? Okay. Now, according to what I just taught you and what all of you already know, most of you already know, to find the GCF of these two things, we take everything that is common to both of them. Is there a 2 in both of them? Yes. So I take the 2. Is there a 3 in both of them? How many 3s are in both of them? 3 cubed. 2 times 3 cubed is 54. So therefore, 54 is the GCF. And that makes good sense, right? Because 54 times 1 is 54. So 54 is a factor of 54. And 54 times 3 is 162. So 54 is a factor of 162. Everybody good? Now, to remind you, GCFs must be less than or equal to the lowest number you're working with. Now that's bad grammar. Please don't punish me for it. I should, of course, have said GCFs must be less than or equal to the lowest number with which you are working. But this is an English class, so we'll leave it like that. Everybody cool? All you do is list out everything that's common, and that gets you your GCF. Now, a lowest common multiple is the lowest number that your group are all factors. You know lowest common multiple as lowest common denominator. You've been finding the lowest common multiple since grade 3 when you learned how to add fractions. Just most of your teachers probably didn't call it the lowest common multiple. They called it the lowest common denominator. Everybody cool? And that can be found using prime factorization. That I'm going to highlight in blue by listing all, not common, all the factors once only. So in GCF, it's all the common factors. In LCM, it's all the factors once. So we're going to take our list again. 2 times 3 cubed. And 2 times 3 to the 4th. Now we're going to LCM that. So I have to list every factor once. Is 2 a factor? Do I need to list it twice? No, just once, because that covers the 2's. Boom. How many 3's does this guy have? 3 3's. Does this guy have those 3 3's? So I don't need to count 3 of those 3's, do I? I got to count them once. But then this guy's a 4th 3, so I have to count 4 3's to cover all of this guy's 3's. Is everybody good? 2 times 3 to the 4th is 162. So 162 is the LCM, which we know makes sense because 54 times 3 is LCM, or is 162, and 162 times 1 is 162. So the lowest common multiple is 162. Is everybody good? Say it. No. 2 times 3 to the power of 4. I have to list every factor once. I had to choose 3 to the 4th because that covers all of this, guys. But I have to remember to count everything once. So 3 times 3 times 3, that covers both of these. And then I got to count that 4th 3. So I count them all. Good? All right. Let's turn the page over and let's make sure. You people do 36. Actually, we'll do 36 and 120 together. Then you're going to do B and C. Then I'm going to make a change to D. So the first thing we got to do is prime factor 36. What 2 numbers can I put here? I could put 3 and 12. What else could I put there? 6 and 6. What else could I put there? 9 and 4. What else could I put there? 2 and 18. Does it matter what I do? No, because at the end of it all, I'm going to have all my prime factors. So I'm going to go 6 and 6, 2, 3, 2, 3. And then I'm done. Right? 2 squared times 3 squared. Then I go over here and I do 120. Doesn't matter what my first branches are. I am going to make my first branches 12 and 10. 2 and 6, there's a prime number. 2 and 3. 2 and 5. 1, 2, 3 2's, 2 cubed, times 1, 3 times 5. And there are my lists, correct? Everyone agree? All right. So now let's do the GCF. GCF is everything common. Is there a 2 common? Yes. How many 2's are common? 2 of them. So I have to count 2 2's. Right? Is there a 3 common? How many? 1. So I have to count 1 3. Is there a 5 common? No. So can I count 5 in this? No. So that is my GCF, which is 12. Everybody good? Now let's do the same thing for the LCM. Is there a LCMs? I have to count everything how many times? Once. Are there 2s? How many 2s? I need to count 3 2s so I cover all of them, right? So I've got 2 cubed. How many 3s covers everybody? 2 of them. So I got to count 2 3s. And do I have to count the 5? Yes, because in LCM I have to count everything. Times 5. 2 cubed is 8. 3 squared is 9. 8 times 9 is 72. 72 times 5 is 360. So that is my LCM. Is everybody moderately okay? All right, now listen. The biggest problem kids have with doing this and what we're about to do when we use this for something is you have trouble doing the division. You have trouble doing the division because you don't actually know your times tables. You say you know your times tables, but you don't actually. Here's what I mean by that. I can say what is 9 times 7. And by the time I finish this sentence, every one of you, without going to your calculator, will say 63. Right? Because you all know that. That's knowing how to multiply 9 times 7. Knowing your times tables means the millisecond that n leaves my mouth, 9 times 7, you have already told me the answer. That's knowing your times tables. Do you understand the difference? If you do nothing between now and when your next math course starts, memorize your times tables. Not know them. Memorize them. So if I say 7 times 6, you've already said 42. Understand? You have not had to do this. 42. Do you see the difference? It is the most important thing you could do to make math easier. When I was your age, they made us memorize them in grade 3. If you can't memorize times tables, you're dumb, they told us. But now, of course, we don't make you memorize anything, because if you are bad at memorizing, that might make you feel bad. And we can't have you feeling bad. That would be wrong. So, take it from me, because I'm not your elementary school teacher. Memorize your times tables. It will make your math go from, math, to, I got this. Okay? Awesome. Now, I do offer a couple of other tricks. All of you have been taught, instead of memorizing your times tables, you were all taught silly little tricks to remember how to do times tables. Like, the 9 times table, all the digits add up to 9. So 9 times 2, 1 and 8. You do 9 times 2, so it's 2 minus 1 is 1, and then 1 plus 8 is 9. You've also were taught something with your knuckles. I don't know what that one is either. And something with counting finger. I don't know what any of those are. Do you know why I don't know what any of those are? Because I memorized my damn times tables. And it is way easier than remembering a bunch of little shortcuts. But since you've been taught a bunch of little shortcuts, there are some shortcuts for division, too. So I'm going to write them over here. You can write them down if you want, or you can just watch the video later. Any number ending in 0, 2, 4, 6, 8, you can divide that by 2. It's automatic. They're even numbers. You can always divide by 2. 2 being a very powerful prime number, right? If the digits add to a sum that divides by 3, then the number divides by 3. Here's an example. 3, 4, 5. 3 plus 4 plus 5 equals 12. Since 12 divides by 3, this divides by 3. That's another very handy one. Okay? Here's another one. If it ends in 0 or 5, it will divide by 5. If it divides by 2 and divides by 3, then it'll divide by 6. There's one more for 9, but I can't remember what it is because I know my times tables. I don't bother learning these tricks. So those might be helpful to you. They're recorded. You can look at them again. You can write them down. I don't care. These two are the most important ones, I think, because they're real easy to check. So you guys do 18 and 24. There's your rules. Go. I, of course, will be making the factor trees up here. And again, I remind you, this is not the third grade. You will be using these skills in the very next 2 lessons, not 5 years from now. Ready? No rush. Hi, Matt speaking. Can I help you? It's one of my favorite ringtones that comes with phones. I love that one. Got a nice beat. You can dance to it. I, of course, don't use any ringtone that came with my phone. Everybody important in my life has a ringtone that is personalized to them. For example, when my wife calls me, it plays the first line to Fat Bottom Girls. Not because my wife has a fat bottom, but because the first line is, "Oh, won't you take me home tonight?" Which is, of course, you know. And when she texts me, it says, "Hello, nurse," which is from Animaniacs, which is what the Animaniacs said every time they saw a hot girl, because my wife's hot. When my daughter texts me, it does the theme from from New Girl, if you don't watch that show. But if you watch that show, you know the theme says, in the song says, "Who's that girl?" So when my daughter texts me, it says, "Who's that girl?" Because my daughter's my girl. When my son texts me, it's the Gravity Falls theme. Because my son reminds me of Dipper. When he phones me, it's Zelda music, because he likes Zelda. Can't remember what it is when my daughter phones me. I think it's that Cake song, "Short Skirt, Long Jacket," because it's my daughter's favorite song. I think. Anyways, back to math. Oh, there's the answer. 6 is the GCF. 72 is the LCM. Can everybody do it? Huh? You count everything that is common. How many 2s are common to both of them? 1. How many 3s are common to both of them? 3. 1. 1, 3, right there. So it's 2 times 3. Okay? I wish for you to try C on your own. When you get to D, I'm adding a third number. It's 35, 84, and 14. Try C on your own right now. It ends in 5, so what are you going to divide by? 5. Now, again, I have to remind you, there are a lot of steps to the math that we do in the 10th grade. Saying that I don't get it makes it really difficult to find out how to help you. So you will notice I have stopped here because I am assuming everybody in the room can get to this point with every question. Is that true? Excellent. So now all you have to do, because you already know how to do this, you don't have to worry about it anymore. You just have to concern yourself with what to do next. Now, what to do next is always a function of what the question is being asked. If I want the greatest common factor, then factors are always smaller than the numbers you're dealing with, right? So if it's smaller than the numbers you're dealing with, that must mean I need the smallest amount of factors here, don't I? What is the smallest amount of 3's? 1 3, right there. So in the GCF, I need 1 3. What is the smallest amount of 5's I am dealing with? 1. 3 times 5 is 15. When I'm doing the lowest common multiple, I need to be bigger than my numbers. So I have to count everything once. What's the biggest amount of 3's I have there? 3 squared. What's the biggest amount of 5's I have there? 5 squared. So that equals 9 times 25, which is 225. Is everybody good? Awesome. Now, what do you think changes if there are 3 numbers? Nothing. When there were 2 numbers, I factored them, made a list, and GCF'd them. What am I going to do with 3 numbers? Factor them, make a list, GCF and LCM them. Right? Because math makes sense. If it works once in math, how often does it work? All the time. Because math doesn't mess with you the way everything else does. So I got 3 numbers here. 14, that's a real easy one. What is it? 2 and 7. And I'm stopping there, right? Because they're both prime numbers. So I got 2 times 7. Yeah. Then I got 35. What's that one? 5 and 7. Nice, easy one. 7 times 5. Then I got 84. Bit harder. It ends in 4, so what can I divide it by? 2. 42. 42 ends in 2. What can I divide it by? 2. 21. What can I divide 21 by? 3 and 7. 2 squared times 3 times 7. Agreed? Now, GCF. It's got to be smaller than 14, doesn't it? Right? So, I got to start at the bottom. 14 is 2 and 7. Is 2 in everything? Nope. Is 7 in everything? Yup. So what's the GCF? 7. Because that was common to all 3. LCM's got to be bigger than which number? It's got to be bigger than 84, because 84 times 1 is 84, right? So it's got to be bigger than 84. So I have to have 2, 3, and 7 have to be counted, don't they? 2 squared, 3, and 7 have to be counted, right? Because that's what gets me to 84. So I have to count 2 squared, 3, and 7. Does that cover this guy's 2? Yep. Does that cover this guy's 7? Yep. Does that cover this guy's 7? Yep. Does that cover this guy's 5? No. Do I need to count the 5? Yes. So I got to add a 5 down there. 2 squared is 4. 4 times 3 is 12. What? Yes. 2 times 2 is 4. 4 times 3 is 12. 12 times 7 is 84. And 84 times 5 is 420. Which is just dumb luck. I didn't actually plan it that way. It's kind of funny, actually, with what is going on in Canada right now. Can everybody do it? All right, now listen to me. Again, this is not the 3rd grade. This is not the last thing in the unit that is what is going on your test. This is the very, very first thing for what we're doing in this unit. Understand? We are going to use these principles all through this unit and all through the next unit. Okay? So, 1 second, Erlen. You have page 90 to work on, and you have a break in, that's a long time from now. It's in 30 minutes. I'm going to give you 20 minutes to work on that, and then we're going to move on to roots while it's fresh in your head. Erlen. Yes, I will go back up. Of course I will. I just wanted to see how much work I gave you there. All right. Any questions from that page? You shouldn't have had too much trouble with it. Any questions? Yes. Fitting. Oh yeah, fitting is badass. Fitting is badass. All right. Okay. Surface area is all the outside, right? So how big is that? X by x, right? Which is x squared. And how many of them are there? 4, because there's 4 walls. So 4x squared, yeah? Okay. How big is that? (5x over 8), right? Times x, correct? Right? Because length by width, yeah? And how many of them are there? 2. Everybody agree? Okay. And then there's this right here, yeah? Which is x, and then I need this height, don't I? Right? How do I find that height? Doesn't that make this triangle? X over 2 and 5x over 8. So can't I do Pythagoras there? Right? So Pythagoras says this side right here is the square root of 5x over 8 squared, right? Because that's the hypotenuse, minus x over 2 squared, right? Okay, so this squared, we just did exponents, is 25x squared over 64, correct? Minus x squared over 4, correct? Everybody's good still? Now, and then all that square rooted, yeah? So now I got to do this, don't I? Can I do this subtraction? What do I need before I can put 2 fractions together? Common denominator, which is 64, right? So this is the square root of 25x squared. We're over 64 minus, how much do I have to multiply 16 by? I get 64 by How much do I have to multiply 4 by to get 64? 16. So that is 16x squared, yes? What is 25 minus 16? 9x squared over 64, right? What's the square root of 9x squared? 3x over, what's the square root of 64? 8. So this distance is 3x over 8, right? That's the height, and the base is x, correct? So that times x, but how many of them are there? 2 of them. So that's 3x squared over 8 times 2, which is 6. Sorry. Cancel, right? So 3x squared over 4. Yes? Because 2 is in the numerator. 2, if I multiply it out, Charlotte, I get 6x squared over 8, right? And then 6 and 8 simplify to 3/4. Does that work better for you? Okay. So I've got to add 3x squared over 4. Does everyone agree? Now all I got to do is work this out. 4x squared. 5x times x is what? 5x squared over 8 times 2 is 10x squared over 8, right? Plus 3x squared over 4. What's this really over? 1. Can I add those 3 fractions together? I can if I do what? Common denominator. What's the common denominator? 1, 8, and 4. 8. So this guy's not changing, is he? 10x squared. This guy to multiply by 8, right? So what's this guy multiplied by? 8. So that's plus 32x squared. Plus this guy to multiply by what? 2. So that's plus 6x squared, right? 10 and 32 is 42, and 6 is 48x squared, right? Over 8. Can you simplify that? How many 8s go into 8? 1. How many 8s go into 48? So it is 6x squared. Oh, they say 45x over 8. I added something wrong then. Something up here. I don't know where. I did it all in my head. I don't know where I made my mistake. But when you get to here, what?
I think it's because when you did the triangle to find the area, you multiply it by 2, when you find the area of a triangle, you divide by 2, and you're multiplying by 2.
Oh, yeah. That is where I made my mistake. But the method is sound. You found all the pieces using lowest common denominator, using exponent rules, and using surface area. And then you would have ended up, if I had done this right, my mistake was in here. My mistake was in here somewhere. But that's what you would have had to do. It's not a matter of being too difficult. It's just a matter of putting it all together, right? If there was no fraction there, you could have done this in your sleep, right? It's the fractions that are messing you up, not the math, right? And that, Charlotte, is why this is the very last question, right? This would be a bonus question on a test. Because would you ever in a million years get measurements for something that had that fraction in it? No, of course you wouldn't. All right. Otherwise, I trust we were good. Sorry, Erlen. 8A. Okay. It's a cube, right? So aren't all of these the same length? And how do you find the volume of the cube? It's LWH, isn't it? Except in a cube, aren't they all the same? So it would be WWW, right? Because they're all the same, right? Well, how do I write that? That's W cubed, isn't it? Isn't it? So W cubed equaled 5832, right? Okay. Well, if W squared equaled 9, what would you do there? You'd square root. Well, W cubed equals that. So what would you do? Cube root, which on your calculator is that. Okay? All right. 12:03 breaks at 12:05. We'll just go on to 3.5 when you guys get back. Take an extra 2 minutes off, but you can't leave the room. Page 91, if you would be so kind. Huh? It's roots and powers, radicals and exponents. Sure. I called it Jeff, but you can call it radicals and exponents if you want. All right. Back to business. As you can see, we are just starting roots now, and I would have liked to have done roots and simplifying radicals in a quiz, but obviously we're not going to get to there. We will be doing roots and simplifying radicals today. You will be quizzing tomorrow. Excuse me. Okay? Okay. How do I find the area of a rectangle? LW. Length times width. Now you've already done this in your previous work. If it's a square, L and W, L equals W, doesn't it? So that must mean this and this are the same. So they're either both L or they're both W, which means if it's a square, instead of doing length times width, we're really doing the side squared. That is why we call it a square root. If you are provided with the area of a square, area equals A, then how do you determine the length of each side? You square root the area. Will give you the side. The square root symbol. Now this symbol, ladies and gentlemen, is called the radical symbol. Because when it's written this way, it's asking for a square root, but it can be written in an infinite amount of ways. So we're going to call it the radical sign, is asking you to find two equal factors of x, whatever is under there. Under where? I did that on purpose, but sometimes I do snort when I laugh. But that one was on purpose. All right. What's the volume of a prism? L, W, H. Right? L, W, H. But what if it's a cube? What do we know about L, W, and H? L equals W, which equals H. So really, this is side cubed equals volume, right? So if we have a volume, which is some sort of units cubed, and I take the cubed root, I get the side length. The same symbol, but with a little 3, means I am asking you to find 3 factors. 3 equal factors. The small 3 is called, and this is important, so I'm writing it in a different color, the index. And I'm highlighting it. The index tells you the number of factors you seek. So if there's no number written there, how many factors? 2. If there's a 3, how many factors? 3. If there's a 7, how many factors? 7. Whatever number is written there is the amount of factors you have to find. Perfect square or perfect cube is any number with a natural root. Okay? Now, I know earlier I said that we can have things like 1.5 or 2.25 and the square root is 1.5. And I said that's a square root, that's okay. It is a square root and it is a rational square root, but we don't like to call them perfect squares. Okay? Because there's decimals all over the place. Everybody cool? All right. Now, you just read that. Square roots and cube roots are another thing, like your times tables, that will make your life easier if you have them memorized. Again, I can't test you on it, but it's a really useful thing to know. Okay? So when you turn the page over onto page 92, I ask you to list them. What's 0 squared? 0. What's 1 squared? 1, 2, 4. 3, 9, 4, 16, 5, 25, 6, 36, 7, 49, 8, 64, 9, 81, and 10, 100. Which of those are the roots and which of those are the squares? These are the roots. These are the squares. Everybody cool? And like I said, I recommend knowing them up to 400. We've gone up to 100. So the next will be 11, 121, 12, 144, 13, 169, 14, 196, 15, 225, 16, 256, 17, 289, 18, 324, 19, 361, and 20, 400. Yeah. But there's also a pattern too. Look closely. Plus 1, plus 3, plus 5, plus 7, plus 9, right? So this one, for example, is plus 31, right? So this one's plus 33, plus 35, plus 37, plus 39. So the next one's going to be plus 41. 21 is 441. But I have those memorized. And I have a few others memorized a little higher up that are helpful, like 30 times 30 is 900, right? But, and again, I remind you of this. I'm going to use an analogy that helps all of you, I hope. You know how sometimes when you've got a million apps going on your phone, it slows down? Right? You guys have all had that happen, yeah? Why do you think that is happening? Why does your phone slow down? Because its processor is trying to do a million things at once, yes? It's using up all of its RAM. Everybody understands this, yes? Math and your brain are the same way. If you have to use up brain power on stuff like square roots and multiplication, is that brain power available for the actual difficult thing that you're trying to do? No, it is not. That is why you commit stuff to memory. That is why when I am doing trig, I do not write theta opposite adjacent. I look at the triangle and I automatically know where theta opposite and adjacent are, and I know whether I'm going to multiply or divide, so I can go straight to my calculator. Why? Because I have that memorized, not because I know how to do it. Does everybody see the difference? This will help you immeasurably. If you choose not to do it, that's okay. But be aware that that means you are using brain power on something that you don't need to be using brain power for. Okay? The cubes, same way. 0, 0, 1, 1, 2, 8, 3, 27, 4, 60. Not 16. 64, 5, 125, 6, 216, 7, 343, 8, 512, 9, 729, and 10, 1,000. Like I say, if you can get those memorized, it will make your life easier. Will it make your life better? No. Will it end world hunger? No. Will it get you that really nice shirt you want from some store that sells $5 shirts for $100 each? No. Will it get you that pair of lucky jeans that cost $200 when they're really $5 worth of jean? No. Are lucky jeans still a thing, or am I too old? They're still a thing? Okay, just making sure. Lucky jeans are jeans that look exactly like every other kind of jean, but they cost you $200 because there's an extra tag on it that says lucky. Or even better, when you guys pay more for jeans that have holes and rips in them. You pay more for less jean. It's kind of like those little Coke cans, too. Oh, I got the baby Coke can. How much was it? $1. How much was the big Coke can? $1. So you paid more for less? Yeah.
They have to put in the work of actually ripping the jeans.
Yeah. It's hard. I do. I buy jeans and I wear them. And then they get distressed. And then they're even cooler. Then what I do is I sell them back to vintage places so kids like you guys will buy my distressed jeans. I don't really, but I should. No, I'm just kidding. You guys go ahead, spend your money. It's not like there's hungry people in the world or anything. All right. Now, listen. We're going to do something with this. We're going to do something with this. We are going to practice estimation because, as was proven by your first unit test, you people never estimate. Which means you hand me in answers that make no sense. This is actually an important call. I need to take this. It will take 2 seconds. So, you have no problem handing in answers that make no sense because you don't ever estimate. So, we're going to talk about estimating here. Square root of 72. Does 72 have a square root? Look on our list. Do you see 72 anywhere? No. What do you see? 81 and 64. So you know that the root of 72 must be hey, I'm teaching summer school. I can't really talk. But okay, I've left the same message with them like 3 times. So, okay. No problem, Sean. Talk to you later. Bye. One day, maybe you guys will have an idiot brother like I have. All right. So, you can plainly see that 72 is between 64 and 81, yes? And you know the square root of 64 is between 8 and 9. So that must mean the square root of 72 is between 8 and 9, yes? Now, how far past 64 is 72? It's 8 steps past, right? So that is 8. How far is 64 to 81? 17, right? So I have gone 8 steps out of a possible 17, correct? 8 over 17 is pretty darn close, approximately 8.5, isn't it? Square root 72. 8.48. Pretty close to 8.5, right? It's a useful tool to have, especially in other classes that use math, right? Physics, chemistry. It's really handy to be able to just have an idea of where you're going. So let's look at 180. Is it on my list? No. What's it between? 13 and 14, right? Because that's the root of 169 and the root of 196. How far past am I? $11. 169 to 180 is 11. And the total distance is almost 30, correct? Right? So I'm at 13, and I'm at approximately 10 out of 30, which is 13 and 1/3, which is 13.3. Is that close enough for an estimate? Square root 180. 13.4, I add 13.3. Everybody see how it works? Great. You do 300. What's it between? And then we check. $17.32. What was our guess? 17.3. Everybody good? $11. Because 300 is 11 past 289. Now, does anything change with cube roots? Does it? No, except the numbers are bigger, yes? They're further apart. So we've got to do even more estimating. 45 is between what and what? It's between 27, which is 3, and 64, which is 4. 45 is 27 is close to what? 30. 64 is close to 65, right? So I'm pretty much 3 and 15 out of 35, right? Which is a little bit less than half, yeah? So 3 point what? 3.4. Let's check. Cube root, 45. 3.55. Still pretty good, right? Everybody with me? Okay. I'm going to trust you to do those two. And then you're going to work on 93, 94. Now listen to me closely, please. And 95. Listen to me closely. On 93, you can use your calculator. All right? With your calculator, if it's perfect, write it. Okay? So I'll give you an example. This first one, I go to my calculator. I do negative square root 196. And my answer is negative 14. It's perfect, so I write negative 14. Everybody good? 27, I already know is not perfect. Square root of 27, 5.2, right? So if it's not perfect, show me, work backwards. How would you estimate that? Square root of 25 is 5. Square root of 36 is 6. It's just a little bit past 5, so you're going to guess 5.1. Does everybody understand? Everybody cool? Everybody's good? Okay, that's what you're going to do for 93. You're going to do that. 94, I'm going to go easier on you. 94, you can use your calculator for the whole thing. And 95, you're probably going to need your calculator as well. On 94, I only need to see the root or the approximate root to 2 decimal places. All right? So on page 93, I want to see those estimates. Page 94, you can just tell me the root or what your calculator says rounded to 2 decimals. Then we're going to do something with page 94 before we go on. We're going to see what time it is before I go on to this. This page should take you about 15 minutes, and then we're going to do some talking about it, which should take us to pretty darn close to the end of the day. If I can get all these tests marked while you're working on this, then we'll finish the day going over the trig test. All right? Go.
right here, since it's 343, I just rounded to 345. So since this one's 343,
So it's got to be between 7 and 8.
Yeah.
Perfect. And, oh, I see what you're doing. Yes. So that's 60, right?
yeah,
So you're 60, and that's basically 340 to 510, right?
yeah,
So that's 17, right? So 6 out of 17, sure, that would be good. Oh, I lost count. Done. There's no square root anymore. It is 14 over 15.
And then here as well, you just do that?
Yeah?
Just put a square root?
No need square root. You've got the square root. The square root of 9 is 3. The square root of 100 is
And then what
10.
about this? Like,
Well, that one you would have to estimate.
Like,
Right? You know the square root of 15 of 25 is 15, 225, but the square root of 48 doesn't have a square root. So you need an estimate there. Right?
okay, then I put 15 and then estimate underneath?
You could do it that way.
Okay.
Yeah, that's what I'm trying to give you guys tools to do. I want to see what you come up with on this page. Hey, buddy.
Where are you going?
Not a lot. What are you doing?
Huh?
How's it going for you?
Huge class. No, nothing. It's going good. Lano's coming. Just lost another student. I think she's struggling. She dropped it.
Who? Which one?
I just lost another student. I think she
I've
dropped
lost
it.
one.
I lost lots, man. They just drop and like, they're going looking at me going, but they're taking like as I said, it's math 10 that they have, and they're taking that and they. So basically, what they're doing is challenging the course, right?
Well, you know, like we tell them every chance we get, right? You've had grade 2 to grade 9 doing the same crap over and over and over again. And now we've got to cram enough to get you ready for university.
Yeah.
Or not even university, let's be honest. You want to be an electrician, you need pre-cal.
I know.
Right?
Yeah.
Like, we have to cram 2 years.
I know,
In
it's
2
so hard.
years.
I know.
Everything that every other country in the world starts doing in grade 3.
I know. I don't know why we made it so. I don't know. It would seem like we watered down a lot of the different, like the grade 8, grade 9. And
Well, you ask exchange students, and
just
it doesn't
watered
have
this.
to be
Hey,
an
they
Asian
covered this.
exchange
They go,
student.
hey, I already covered that.
Yeah.
You know?
You ask a kid from Brazil.
Yeah.
When did you guys do this? Grade 5.
Yeah. Exactly.
Because when they were taught something, they moved to the next thing.
Yeah.
We weren't.
No.
Oh, you still don't know how to add fractions? Well, we'll put it in the next year too. And the next year, and the next year, and the next year. Oh, wait a minute, you have to know how to add fractions. Maybe we should have made you learn that in grade 5.
Exactly. No, I have a kid. He's in the bathroom for 15 minutes. I walk in. Hey, Brandon, are you in here, sir? Yeah, I'm still here. I go, okay. Because he disappeared. That's why I'm walking by. Because he disappeared for 15 minutes. I go, I gotta go check and see if he's still in the bathroom. He wasn't feeling well, so I guess
That happens.
I guess he's still I know, hey, you're not feeling good.
Darby. A, B, D, B, B. Mr. Brar.
I don't understand how to do this.
Well, I just showed you, didn't I?
What about
Is that a perfect square?
no?
No, so you do what we just did. It's between 25 and 36. 5, it's just a little bit past, so 5.1 would be a good guess.
I mean, like 5 is just past. What does that mean?
Well, 27 is just past 25. 25's root is 5. So 27's must be just a little bit past 5.
It's 5 point.
Yeah. This one. Square root of that whole thing, right? So that means I got a square root 9 over square root 10. What's the square root of 9?
3,
What's the square root of 10?
10.
Or square root of 100? 10. Done. It's perfect. Is that one perfect? That must be the square root of 225 over the square root of 48.
Yeah.
225 is perfect, that's 15, but 48 isn't. But it's almost 49, isn't it? So that's almost square root of 49, which is 7. 15 over 7 is just a little bit more than 2. Okay? Figure it out. That's the whole point of it. Yes. Okay, listen up. Oh, I'm only 3 tests away from being marked. Keep working for 2 seconds. I'll finish these last 3. I'll go over these sheets, then we'll go over the test. No, my Hindi is pretty rusty. I can't speak a word of Hindi. Or Punjabi. Not a word. Sign out. You already went out.
Stick it 2 minutes.
Time's tough all over, buddy. Only takes 2 minutes to put a bunch of crap in the urinal, too.